Hello, welcome to Maths with EJD. In this video, we'll be talking about derivatives and integrals of hyperbolic functions. Okay, let's start with derivatives. Derivatives of hyperbolic functions. Okay, the derivatives of hyperbolic functions are similar to their are similar in form to their trigonometric counterparts, but with distinct identities. Sure, as derivatives go, let's start with sin x. Normally, right, we know sin x is actually the same thing as e raised power x minus e raised power minus x divided by 2. So normally, if you're going to differentiate this, that means you're saying d dx of sin x. Okay, maybe this is better. D dx of sin x, and that is d dx of e raised power x minus e raised power minus x, all divided by 2. So that means we have d dx of half e raised power x. We can split it apart, minus 1 over 2 e raised power minus x. And then that means when you differentiate e raised power x, of course, you get the same. So half is there as constant. So you have half e raised power x. Then when you differentiate e raised power minus x, of course, that is going to be minus. Of course, the half is outside. So bring this half outside. Then when you differentiate e raised power minus x, differentiate minus x, you get minus 1. So the minus comes down, and then you still have minus e raised power minus x, like that. So, and that means you have half e raised power x, minus times minus is plus, half e raised power minus x. So that means if you take the LCM again, you have e raised power x plus e raised power minus x divided by 2. Now, does this look like what you've seen before? I am sure yes, because this is simply cosh. This is simply cosh x. And that is to tell us that d dx of sin x will give you cosh x. So that's a very, that has been proven. So I won't worry talking about the same for the others. So I'll just go straight. So if we take this example that if f of x is sin 3x, then f prime of x would, so differentiating this would simply mean that, of course, you already know differentiate sin x, you get cosh x, but then you have 3x. So differentiate 3x, you get 3. Then the 3 will have to multiply the cosh x that you would get. So that goes like that. And then we talk about the next one. That's number 2. When you differentiate, so I'm just going to write for the rest, so I don't just spend any time trying to work those things out. So we just go through the normal procedure for differentiation. So d dx of cosh x is actually the same thing as sin x, So you can do the same process like I did before, and then you get that. So that's sin x. So that should be clear, so that if we take this example that if g of x is equal to cosh 2x, then if you differentiate this, then g prime of x would be 2. The differentiate sign, you get a cosh, you get sinh. So that's sinh 2x, and that goes. And then we go for number 3, which is tanh x. Tanh x. When you differentiate tanh x, what do you get? So just like the form, like we already know, the form is like that for tan. So if you don't understand trig, I have a whole playlist on trigonometry. So you want to check the playlist and refer to it so you understand the form thing we're talking about. So d dx of tanh x is actually the same thing as sesh squared x, like that. So that if h of x is equal to, if h of x is equal to tanh 4x, then h prime of x would simply be 4 sesh squared 4x, basically. So, and then we move on to the next one, number 4. Let's talk about cosh x. So cosh x is simply this. If you differentiate cosh x, so it gives minus cosh squared x, basically. Yeah, basically that's what that gives. So that I feel like doing this. I wonder why. I feel like doing this. Okay, let's do it. So, but this is the basic thing. So to do that, right, we already know that cosh, you know that cosh x is actually is tanh x is actually the reciprocal actually of tanh x. That's 1 over tanh x. And you know tanh x is the same thing as sinh x all over cosh x. So that means that cosh x is simply the same thing as cosh x all over sinh x. Okay, so just bring the expression. So cosh x up there is e raised power x plus e raised power minus x divided by 2. Then all this divided by sinh x, e raised power x minus e raised power minus x divided by 2. So that we have e raised power x plus e raised power minus x divided by 2 times 2 all over e raised power x minus e raised power minus x. So this cancels out. And then we have cosh x to be e raised power x plus e raised power minus x all over e raised power x minus e raised power minus x. So this is the expression now. So to differentiate this, right, we can see that is actually, we can do product, we can use quotient rule or product rule, anyone you choose. So to use quotient rule, for instance, this is u and this is v. So it means that d dx of cosh x would just be, so of course that'll be like v du dx minus u dv dx all over v squared. Okay, so that means that the derivative of cosh x is v, this is e raised power x minus e raised power minus x du dx. That means differentiate the one at the top. If you differentiate u, you get e raised power x minus e raised power minus x. As you can see, differentiate e raised power x, that's e raised power x. Differentiate e raised power minus x. So that means differentiate minus x, the minus comes down, and then you have what was there before. Then minus, okay, I guess I want to start from the very beginning so I can have a lot of space to take care of this. So I bring it back here. So I bring it down here. So v is e raised power x minus e raised power minus x settled. And then we have du dx, that's differentiate the one at the top, that's e raised power x minus e raised power minus x minus u itself is e raised power x plus e raised power minus x. dv dx, that means differentiate the bottom, e raised power x remains. Then there's minus a differentiate e raised power minus x, that's minus e raised power minus x, that's minus, that's plus e raised power minus x all over whatever v is e raised to power x minus e raised to power minus x all squared. Okay, so that's the cosh x going. So we have d dx of cosh x, d dx of cosh x, and that is equal to, so these two are the same. So we have e raised to power x minus e raised to power minus x minus e raised to power minus x all squared minus e raised to power x plus e raised to power minus x all squared, because they are basically the same. And down here we have e raised to power x minus e raised to power minus x all squared. So what can we do here? Okay, well, there are many things we can actually do. There are many things we can do. I'm trying to decide the best. Okay, so we know that we can actually split this up, right? We can split this up. I'm thinking of expanding. Let's expand and see what happens. So if we I'm wondering which one is going to be good. There are many ways, but let me go the division way. So we'll just have e raised to power x minus e raised to power minus x all squared divided by e raised to power x minus e raised to power minus x all squared. Then minus e raised to power x plus e raised to power minus x all squared divided by e raised to power x minus e raised to power minus x all squared. Now you can see these two, this and this are basically the same. So these two will give us 1, but this is not that. But we can see that this is e raised to power x plus e raised to power minus x all over e raised to power x minus e raised to power minus x all squared. Now this looks like an expression we must have come across before. So e raised to power x plus e raised to power minus x. So that looks like where we are coming from. I want to think, cosh x is e raised to power x plus e raised to power minus x all over. So it means this whole expression. So this is 1 minus, this whole expression is actually cosh squared. Okay, well, let me go slowly. This is cosh x all squared. So that means we have 1 minus cosh squared x. And I'm very sure there's an expression that holds this together. There's a general expression that cosh squared x minus sine squared x is equal to 1, right? So we know the result for this is actually cosh squared x. So let's see what that gives us. So of course we are still talking about d dx of cosh x. Okay, d dx of cosh x. So we know already that okay, this is cosh squared x right here. We know there's an expression that cosh squared x minus sine squared x is equal to 1. That's like the hyperbolic identity or whatever you want to call that. But this is cosh now. Okay, let's do it this way. So we have 1 minus so this is cosh is actually 1 over tanh. Yeah, we can do it that way. Cosh is 1 over tanh squared x. It can be that. And we know this is 1 minus 1 over sine squared x. I wonder why I'm trying to do this. I just feel I should explain this somehow. So this is 1 over 1 minus cosh squared x all over sine squared x. So the LCM, of course, is sine squared x. So 1 here times 1, that's sine squared x minus up there we have cosh squared x. So you can see this is more like so if we factorize 1 out, if we take 1 out, that's minus into, so if we multiply through by minus, so I will take the minus out, so this can turn to cosh squared x minus sine squared x. You understand? So 1 minus cosh is 2 minus and minus, that's plus, so that's fine. And then we have sine squared x. So, and we already know from this expression you got up here, cos squared x minus sine squared x is 1. So it means that this expression, this whole expression is actually 1. So we have minus 1 over sine squared x. And the reciprocal of sine squared x is actually cosh. So we have minus cosh squared x. And that is why the derivative of cosh x is actually minus cosh squared x. So that's that. I just felt I shouldn't just write that down. So you can use the same idea for tanh x and all that. Okay, so having done that, let's talk about okay, well, let's for tanh, did I just do tanh and just get past like that? Tanh for tanh. Okay, well, for tanh, right? Okay, h of x. Oh, okay. Okay, I'm jumping ahead. Okay. Well, I'm in order. Yeah, I'm still in order. Correct. Okay, so that is how you differentiate cos squared x. Probably if you check again, you can see faster ways of arriving at the answer. But I mean, this is one way. So that's cosh squared x, cosh squared x when you differentiate cos squared x. So let's take the fifth one. The fifth one is the derivative. Let's talk about the derivative of sech x. Derivative of sech x, that's d dx of sech x. Okay, I'll just write this down. This is minus sech x tanh x. So if you want to try that out, just know that sech x is the same thing as 1 over cosh x. I know that cosh x is e raised power x plus e raised power minus x divided by 2. So you know, you just reverse it and do the differentiation, just like what I did now. Okay, so that is what you have for sech x. Okay, well, since I've taken plenty of time here, should I still do this? Okay, let me see. So if you have this example, talking about cosh x now, if p of x, that's the same example I've been doing for everything. If p of x is cosh 5x, then p prime of x would simply be minus 5 cosh squared 5x. Okay. And then here we have minus x tanh x. So if that is the case, we can say that if q of x is equal to sech 3x, then q prime, that's the derivative, q prime of x will be minus 3 sech 3x tanh 3x, like that. And then we have the sixth one, talking about the derivative of cosh x, which you can also handle by writing it out explicitly and then going through the motions of differentiation. So you have the dx of cosh x, that is given as minus cosh x cosh x, minus cosh x cosh x, like that. So if we take, for example, that r of x, if r of x is cosh 2x, then r prime of x is minus 2 cosh x cosh 2x, cosh 2x cosh 2x, and that goes. So with that, we come to the end of differentiation of derivatives, or differentiation rather, or differentiation actually of hyperbolic functions. So let's quickly talk about the integrals. Integrals of hyperbolic functions. So integrals of hyperbolic functions. So integrating hyperbolic functions often follows directly from their derivatives. So if you know the derivative, then the integral is easy. So just master the derivatives and the integrals will just come naturally. So for instance, for number one, if you have to integrate sinh x as usual, want to integrate sinh x, that's the integral of sinh x. You know, if you differentiate sin x, if you differentiate cosh x, you get sin x. So that means that if you integrate sin x, you should get cosh x back. You know, because integral is the reverse of differentiation of derivative. So if you integrate sin x, you should get your cosh x back, of course, plus a constant, which is arbitrary. So, for example, if you have integral of sin 2x dx, in this case, you know, in the case of differentiation, it will come as 2 outside. But in the case of integration, that will be it will be 1 over 2, you know. So differentiate 2x, you get 2. But for integration, it becomes half. So you have to put 1 over 8. So you have half cosh 2x plus c. So that's how that goes. Then number 2, you have cosh. You have cosh x now. So integral of cosh x dx. So you remember, if you differentiate sin x, if you differentiate sin x, you get cosh x. So it means if you integrate cosh x, you should get your sin x back. So you have sin x plus an arbitrary constant, such that the integral of cosh 3x dx would simply be 1 over 3 sin x plus an arbitrary constant c. Okay, and then we have the third one, talking about tan x. So once you know the differentiation, then the integral just follows from that. So you know that if you differentiate tan x, what does that give again? The derivative of tan x, you know, that's sine over cos. So that's like, let's see, if you differentiate tan x, you get sec squared x. And you know, sec squared x is just like 1 over cos. 1 over cos. Okay. So in this case, it becomes, so log comes into the matter. So you have tan x now. So if you integrate tan x dx, you have the log of cosh, of the absolute value of cosh x. You know, log only happens for negative signs, negative values. That's why we need the absolute value of that expression. Because, of course, I think it's easier to look at it from the viewpoint of, okay, I feel I should do this. I actually feel I should do this. Let's go for it. So we have integral of tan x dx. So, you know, that's the same thing as integral of sin x all over cosh x dx, because tan is sin over cosh. So I want to integrate this, okay? So one thing we can do is we can say, yeah, you know, there's under differentiation, right? There's this idea that if you differentiate this and you get this, then the integral is the log of the bottom. Do you understand? So if you integrate cosh x, you're going to get sin x. So it just follows that the integral will be the log of the bottom. So that's which you differentiate to get the one at the top. So plus c. So I think it's even easier than what I was expecting to encounter. So that's how it goes. So just know that tan is sin over cosh, and then the rest goes so easily. So we talk about the fourth one, I believe. Yeah, the fourth one is cosh x. So integral of cosh x dx is equal to, of course, you know, cosh is cos over sine now. And if you differentiate sine, you get, if you differentiate, cosh is cosh over sine. And if you differentiate sine, you get cosh at the top. So this is just going to be the ln of the bottom, which is ln of sine x plus an arbitrary constant c. Okay, for here, right? For tan, I forgot to do this. Like, imagine you have this example. Imagine you have this example that the integral of tan 4x dx. Of course, that's going to be 1 over 4 ln cosh of 4x, plus c, like that. And then for cosh now, imagine that you have this one. You have, for cosh, you have integral of cosh x, cosh 2x dx. So that'll simply be 1 over 2 ln of absolute value of sin x plus c. And that goes. Then number 5 now. Number 5, you want to integrate sech x. So to integrate sech x, now that's the integral of sech x dx. So in this case, when you differentiate, what do you differentiate to get sech? I think that's key here. So, and if you do all this, it leads to 2 arctan. Oh, actually 2 arctan, 2 arctan of tan x over 2. That's what happens here. So 2 arctan of tan x over 2, like that. Then, okay, so you have an example. Integral. So if you want to do the integral, I'm talking about number 5, right? Yep. So that is, if you have sech 3x dx, that is equal to 2. There's this 2 here before, and this 3 comes under, that's 2 over 3. Of course, you can also write arctan. So you can write arctan this way, or you can say it is arctan like this. So either way is fine. So you have 2 over 3 arctan. I prefer to write it this way. I just like it. Like, I feel it's cuter this way. Then you have tan 3x over 2 plus c. And that goes. And number 6, finally, number 6, you have number 6, you want to talk about the integral of cosh x. So the integral of cosh x dx is equal to ln of the arc of tan x over 2 plus arbitrary constant c, such that if you have an example that the integral of cosh, the integral of cosh x, or rather cosh 4x dx, that is 1 over 4 ln tan 2x plus c, like that. So that goes. So finally, in all this, we can also refer to how you can use this to solve differential equations. So let's talk about solving differential equations, solving differential equations with hyperbolic functions. How do you do that? So hyperbolic functions, one day in the future, I'm going to make, at some point in the future, I'm going to make videos on differential equations. So watch out. So hyperbolic functions often appear in the solutions to differential equations, especially when dealing with second order linear differential equations. Okay. For instance, let's look at if you have, okay, let's check out some examples. So one, consider the differential equation. Consider the differential equation d squared y dx squared minus y equals 0. Of course, this is the second order differential equation because it involves second order derivatives. Of course, a differential equation is an equation involving derivatives of a variable with respect to another variable. So if you look at this now, normally we would say let y be equal to r, something like that, and then you continue, you keep working, and then you end up getting r squared minus 1 like that. So we say so in this case, the characteristic, I'm still going to deal with this properly in the future, so watch out. So the characteristic equation is r squared minus 1 for this. So because this is power 2, you have r squared, and this is like zeroth derivative, so to speak. So you have r squared minus 1 equals 0. So, and then that means if you find r here based on this, now r minus 1 into r plus 1 equals 0. So it will give us roots. So the roots will be r equals plus or minus 1. So the general solution, anytime you have this now, the general solution would be y of x, which is equal to c1 e raised power x plus c2 e raised power minus x. And of course, you can already see that looks very much like, you can see e raised power x, e raised power minus x, and all that. So that looks pretty much like e raised power x plus e raised power minus x. That looks a whole lot like some constant multiplied by cosh x. So you see that coming up in differential solutions to differential equations. Okay. So another example will be this. So for the differential equation, for the differential equation, which is d squared y dx squared minus 4y equals 0. Again, the characteristic equation, the characteristic equation here is actually r squared minus 4. That's how this pans out. So you have r squared minus 4, which is 0, with roots r equals plus or minus 2. And the general solution is y of x, which is equal to c1 e raised power 2x plus c2 e raised power minus 2x. And all of that boils down to something like, oh, okay, up here, I think I did not complete it. So this is actually c1 cosh x, cosh x plus c2 sin x. Apologies. That's what the solution for the first one looks like. C1 cosh x plus C2 sin x. Then for the second one now, we have this to be equal to C1 cosh 2x, C1 cosh 2x plus C2 sin 2x, like that. So you see how useful that is. So finally, let's talk about applications. Let's talk about applications in calculus. So applications of derivative and integral of hyperbolic functions. So applications in calculus. Okay, we have a couple of them. Hyperbolic functions have various applications in calculus and related fields. The first one is arc length. So if you want to find the length of an arc, hyperbolic functions can be really useful. So the arc length of certain curves can be calculated, can be calculated using hyperbolic functions. Using hyperbolic functions. For instance, the arc length of the catenary curve, that's like a cable hanging on a pole. That's what a catenary is. So for instance, the arc length of the catenary curve y equals a cosh x over a is length equals the integral from x1 to x2 of the square roots of 1 plus sine squared x over a, all that dx. So once you integrate this, you're going to get the length of the catenary. So that's something. So if you work with cables hanging on two poles or something, so this is a very good, this is very useful for you for talking about application. Okay. So then another one would be this surface area of revolution. Surface area of revolution. Surface area of revolution. So here, when revolving, so I talked about this under basic calculus when I treated integration. So you want to revisit that playlist too. When revolving a curve around an axis, the surface area can be computed using integrals involving hyperbolic functions. Then, of course, we've seen an application in differential equations just now. So we saw an application for differential equations. So let's talk about that again. Differential equations. Okay. So here, hyperbolic functions are often solutions. They're often solutions to linear differential equations. Linear differential equations, especially in physics, for modeling wave equations. Heat conduction, wave equations, heat conduction, and more. And lastly, we have relativity. That's some physics talk, and hyperbolic geometry. So talking about hyperbolas rather. And this has applications like, I think Pringles, the Pringles has the shape of a hyperbola, and all of that concept, that shape of Pringles is actually obtained from all these things you're doing. So relativity and hyperbolic geometry. So in special relativity, hyperbolic functions describe the relationship between space and time coordinates. particularly in Lorentz transformations. So all these examples actually illustrate the significance of hyperbolic functions in various aspects of calculus and their practical applications. Thank you for always stopping by. If you have not subscribed, be sure to do that. Hit the notification bell too so you can get alerted each time a new video is released. And do not forget to comment, like, and share. See you next time. Bye.